And maybe half of the time it's people just running a stop sign. We see a lot of that. Half of the time it's, hey, there was a stop sign, but actually it was not for you. It was for the oncoming traffic. And the stop sign was just angled way too much, and it looked deceiving to the neural network. And so both would be coming back in this stream of data.
Now, another thing that I've heard you talk about, and that just sounds really intriguing, ties into all of this, is this thing called Operation Vacation. What is Operation Vacation?
In the process of iterating on all these predictions in the team, we are noticing that more and more of its components can be automated. So as I described the process, your neural network makes predictions. You need to source at scale mispredictions, annotate them correctly, and put them into training set and retrain the network. That's the loop. And we're noticing that you can involve engineers less and less in that loop, and through a lot of automation. Now, it's not all the engineers that get to eventually go on a vacation once we've automated the whole thing. There's a large data labeling team who has to stick around, monitor the triggers, and annotate the data. But the actual software engineers who write code could, in principle, go on a vacation, having automated all the pieces of this improvement loop. So I would say it's kind of like a half-joking North Star for the team, where once these neural networks are just getting better by themselves, with a lot of people in between, but just data labelers mostly, we get to all go on a vacation, and the autopilot could, in principle, just improve automatically.
Are you worried, though, that Elon might let you be on vacation for the rest of your life?
We may be able to get away with a few days. We'll see. I'm not sure.
It's so interesting because it also reminds me of when you were actually visiting Covariant, you said something along the lines of the data annotation is what you spend all your time on, and the data annotation playbook is so valuable. It's the thing that generates so much value, right? Which is something that somebody in academia, of course, would never even pay attention to. But Operation Vacation sounds exactly like that the people who are still working are the ones who are working with the data, and everybody else is on the beach, I guess.
It is done half-jokingly. Actually, as I described the system, there's plenty of design and engineering that can still go into the fundamentals. Like, as an example, the system right now makes all these intermediate predictions, and there's still a lot of human-written code on top of it. And this human-written code is very difficult to write, and it's brittle, and it will not fundamentally, I think, scale to where we need it to be if you really want 99.99% of accuracy and comfort. There's some challenges that sort of remain, I would say, on the modeling front, and so we'll be busy with those. But if you're just talking about the perception system itself, I think its improvement can be just improved autonomously just on the raw detection itself. But yeah, as you mentioned, data annotation is not something you would do as a deep learning engineer, and we spend a lot of time on it. I actually have an entire data labeling org that we've grown inside Tesla, because this is so fundamental to what we do. A typical approach would be that you outsource it to third parties. We don't do that. We have a highly professional, highly trained workforce that curates our data sets, and we think that this is the right way to go, because this is just a new software programming paradigm. Again, these are our new programmers in the software 2.0 land, and so they have to, when they're annotating examples, they're telling the system how to interpret the scene, and they are quite literally programming the autopilot. So we invest quite a bit into the org, and we keep it close, and they collaborate with the engineers very closely.
That's amazing. Now, when I think about data annotation, I mean, immediately the other thing I'm thinking about is self-supervised learning, which has made a lot of progress in AI in the last 2-3 years, both in computer vision and in natural language processing, but probably here the vision part is more important. And so I'm curious about your thoughts on the role of self-supervised learning. Maybe you can first define for our listeners, what is self-supervised learning?
Here's the issue with the current technology, basically, is I can get almost any arbitrary deduction to work at this point, and this is just technology, but I need tens of thousands of examples for it. So if I need to recognize fire hydrants, absolutely doable. I need 10,000 examples, 50,000 examples, and I need to do a bit of data engine to pad out the data set, and I know this will work with a neural network. It's just technology. But there's a lot of things you want to recognize, and it feels silly to have to redo this work of like, hey, 50,000 times, this is a fire hydrant from all the possible rotations and all the possible brightness conditions. It just seems so silly. And so this is where the analogy again with the human brain breaks, in that for a person, you show them a fire hydrant and they sort of get it. It's the yellow things on the side of the road. That's not how our current technology works. It needs a really good coverage of fire hydrants. And so that's why a lot of people are perceiving basically there's almost like a flaw with the technology right now, and they're trying to come up with ways that will not require that huge amount of annotation. So maybe with very few examples, the neural network, just like a human network, should already sort of like know about fire hydrants, and you're just telling it, hey, that yellow thing on the side of the road, you don't need 50,000 examples, you need very, very few, because the network already sort of understood fire hydrants, and now it's just getting a label for the thing it already has a neuron for. And so it's much more efficient at the use of the data set.
So Andre, when you say the network already kind of understood fire hydrants, but was never told what they are, but where does that sort of understood it already come from?
Exactly, so that's where self-supervised learning is about, is how do you train on a large collection of examples that did not have to go through a human annotation effort. Maybe people didn't go in and they didn't put bounding boxes around fire hydrants. Maybe it's just a huge amount of data and fire hydrants are featured in some of it. And maybe there are other objectives than explicit matching of human annotation that we can use to pre-train these networks so that they develop these representations. So there's many ways that people are trying to arrange it. As one example of many that seems to work relatively well is, for example, you could try to predict the future. And so it's not that we don't use labeled data, it's that we are using data that is annotated for free. Because when you have a video of what happened in the world, you sort of have the future and came for free in the data stream. So you're still training the network to predict a thing, just like normal supervised learning, but you happen to have that thing for free without human effort. And so self-supervised learning is a class of approaches that try to leverage the structure of the data and try to take advantage of the free supervision that we have just in raw data streams, instead of to sort of get the networks to arrange themselves into configurations that kind of understand the world, so that it's much more efficient per label to train anything else. Fire hydrants may not be like the best example, but yeah, as an example to predict the future, you have to actually understand the layout of the entire scene and how people and cars move and interact. And so this prediction problem forces the neural network to understand that, hey, there are cars, they move around, there are people, they move around, they avoid these areas. And so when I need to predict the future, I need to actually parse the scene to do that properly. Yeah, there is a class of approaches, and we have tried a number of them. I do find that in these incredibly valuable applications, just paying for the labels is often the right way to go, instead of paying researchers. But I think I basically kind of agree with that. Yeah, this is, it's not ideal. And there are some techniques that, as you mentioned, are seeing quite a lot of traction. And we have experimented with a number of them internally at Tesla.
That's really exciting because, I mean, the way I also see is that once you go self-supervised, you can use infinite data effectively, because all data works, right?
You have to be careful though, because more data is not always better. If you add boring data into your data set, you may actually be diluting your data set, right? Because your neural network will train for, like I mentioned, 3 weeks, and it's going to see some number of examples in its training. And if a lot of the examples are boring, it's not going to learn a lot. So you actually want to be very careful with and this is why I talk about curation of data sets. It's an active process of adding hard examples and subtracting the easy examples often. And a very easy way to see this is, of course, if I had just a single image in my massive data set, of course, that's not helpful. So you really want to pad out the variability. And that's why I use active terms like curation when I talk about data sets. It's an active process to curate the data set.
One thing that Tesla has also announced is building their own chips for AI compute. Why does that matter?
So there's many possible answers to that, of course. I think to a large extent, Elon sees AI as just a fundamental pillar of a lot of this technology and wants to invest into internal teams that develop a lot of this technology and co-design everything. Tesla is definitely about vertical integration and squeezing out a lot of juice from the benefits of that. To a very large extent, of course, we own the entire manufacturing of the vehicle in the factory. And then we own a lot of the pieces of, the hardware itself, how's it pointed, all the design decisions. And we own the cluster, we own the data labeling team, and also we own the inference hardware, the chip that actually runs the neural network on the car. To us, it's just another opportunity to co-design everything, specifically for the purposes of self-driving. And so the chip is designed with the kinds of neural networks we want to run in mind, and the hardware itself is just targeted to the operations that we want to run and do that very efficiently. And so really it's a theme of Tesla, and it allows us to co-design all the components to work together towards a single goal, in this case, full self-driving.
When I think about chips for AI compute, I tend to think there is training, and then there is inference, as you alluded to, which is when it's used for driving. Are you using both? Is it just inference right now?
Yeah, good question. So as you mentioned, you will typically I guess hardware for deep learning actually kind of has like two broad areas now. There's hardware you would use to train neural networks, and that looks very different from the hardware you might want to use to run a neural network. So running a neural network is computationally much more straightforward thing. The neurons just have to fire in a sequence. If you're training a neural network, there's a lot more that goes on there because you have to run the neural network forward, but then you also have to implement the backpropagation algorithm, and you have to run the backward pass, and you have to update the weights. And there's a lot of technical details as to like at what precision do you run all this mathematical precision in terms of the numbers involved. And so there's a lot of details that make the training a much more heavy endeavor, and the testing, the inference, a much simpler endeavor. And so, as you mentioned, we currently have a chip for inference that we own and we've designed and is in all the cars. And we are also working on a training computer, and this is Project Dojo, and Elon has sort of alluded to it on a high level a number of times. And it is really just pushing this co-design even further. And we have a rough understanding of what these computational workflows look like for training neural networks for the autopilot. It's a massive amount of video training. We are building a chip directly sort of designed for that kind of a computational workload. And so, yeah, that's absolutely an active project currently at Tesla.
I'm curious about your thoughts. I mean, you were at OpenAI, you're one of the founding members, and OpenAI somewhat recently raised $1 billion with specifically compute in mind. And so I'm curious about that strategic angle also. Is that something on your mind, that more compute is the only way to succeed in AI?
Yeah, I think more compute is one of the fundamental limiting blocks right now for a lot of things, for a lot of domains. OpenAI is right now focused on, for example, natural language processing, for example, with their most recent work on GPT. So what they're doing there is it's a language modeling task where the neural network is generating language text. And so you can feed it text and it will continue text, or you can ask it to produce text with certain properties, or it will answer your questions, or it will talk to you. So what's happening there is the algorithms, again, in this setting are actually quite well known and understood. As you mentioned, the neural network takes the form of this transformer. You're training it in a very kind of standard regime with backpropagation, stochastic gradient, and so on. So that's understood. So the algorithms are not the bottleneck for them. The data set is also not a bottleneck for that class of problems because we have the internet with a huge amount of text. So in that regime, also you are not upper bounded by data sets, but you are upper bounded by the compute available to you, which really restricts the size of the model that you can actually use. And like I said, in deep learning, we are blessed with algorithms that seem to continue to work better and better as you just make them bigger. You're literally just adding neurons into the system and it works better. And so OpenAI is primarily gated by compute in this setting. If they could train a bigger network, it would work better. And that's not the way it used to be in AI. We used to be bottlenecked by algorithms. And so what a beautiful place to be. If they could just run a bigger network, it would work much better, and the results would be even more magical.
And is that true for Tesla also?
Yes, I would say so. And neural networks have this property in general that, yeah, if you make them bigger, they will almost always work better. And, you know, in the limit, you can, for example, use, this is slightly more technical, but you could use model ensembles, you could use dropout, and a lot of techniques to basically make sure that these models work in the world.
You absolutely did. In San Francisco. Hello, my name is Peter Abil, and welcome to the Robot Brains podcast, a show about AI and robots and the brilliant brains who make them. Today, here with me is Andrej Karpathy. Andrej is the Director of Artificial Intelligence and Autopilot Vision at Tesla. He's one of the world's leading visionaries in deep learning and computer vision. Ever since his PhD days at Stanford, back when deep learning was just starting to emerge as a viable technology, Andrej has not only been a leading researcher, but also a leading educator. From there, he became one of the founding members of OpenAI, the AI research organization in San Francisco, initially largely funded by Elon Musk. And from there, at some point, Elon Musk then recruited Andrej to head up autopilot efforts at Tesla. Andrej, you and I used to spend so much time together. For listeners, Andrej and I used to work together at OpenAI, but we also used to see each other at all of the AI conferences, academic working groups. But now it's actually been quite a while since we've seen each other, so I'm excited to get to catch up. Not even sure when is the last time we saw each other. Maybe NeurIPS, maybe my wedding, maybe Covariant offices. Do you remember?
I do. It was just before the pandemic, I think.
Right before pandemic? Must have been at Nirup's in Vancouver. I remember the burgers we went to eat in this dive bar across the conference center.
Yeah. And of course, I visited Covariant and saw your offices, and we had a chance to talk there.
Which was a lot of fun. I hope we can host you again sometime soon. I actually spent most of yesterday watching all the videos listed on your website. Absolutely brilliant what you've achieved and how you explain it there. Now, can you tell our listeners a little bit about how you went from Slovakia, age 15, to becoming Tesla's AI director?
That's a quite all-encompassing question. Yeah, it's a long story. So as you mentioned, my parents decided to immigrate to Canada when I was 15. Yeah, I was not a very happy sort of person in Slovakia. I always wanted to leave. Slovakia is not an incredibly ambitious place. I felt that I was upper bounded in terms of what I can achieve there. And so I always wanted to go to Canada, America, and do something substantial. When they kind of hinted that we may be able to go to Canada, I was on board instantly. And then my sister was not quite as on board, and everyone else in the family as well. But I sort of worked to convince everyone and make the move. We came to Canada. I started in high school. I barely spoke any English. I had to learn English. I was very good at math. Luckily, the Slovakian curriculum is quite good at math. And so I was able to sort of get into their good courses and go through high school, join the University of Toronto, and kind of get into computer science and so on. It is a long story.
It is a long story, but I think there are some really interesting parts to it. For example, somewhere I read that Jeff Hinton at Toronto is the one who first showed you neural networks.
Yeah, so in the University of Toronto is when I first came into contact sort of with deep learning through Jeff Hinton's class. And he taught a class, and at the time, this was very, very simple primordial deep learning. So we were looking at little digits, white on black, 3, 2, 4, 1, and we were trying to recognize, those digits. And so by today's standards, these were incredibly toy problems. I was fascinated by the way that Jeff Hinton spoke about these algorithms. He kept making analogies to the human brain. And, the way he talked about the neural net, it was like in the mind of the network. And he kept using these anthropomorphic descriptions for what was going on in the algorithm. And I found that analogy fascinating. And so that's kind of what pulled me in, I would say, into the entire area. And then I audited the class, and I also went to some of the reading groups that he hosted with his students. And that's basically when I became extremely interested in deep learning and have been in deep learning since.
Now, if we jump ahead a little